Our first speaker is Dr. Gina Sigler. She is a contractor with Huntington Ingalls Industries and is the DoD Program Lead at the Scientific Test and Analysis Technique Center of Excellence, STAT COE. She has been working at the STAT COE since 2018, where she provides rigorous test designs and best practices to programs across the DoD. Before joining the STAT COE, she worked as a faculty associate in the statistics department at the University of Wisconsin-Madison for 3 years. She earned a BS degree in statistics from Michigan State University, an MS in statistics from the University of Wisconsin-Madison, and a PhD in applied mathematics statistics from the Air Force Institute of Technology. Please welcome Dr. Sigler.
All right, so this is actually my PhD research. So as Corinne said, I'm with the Scientific Test and Analysis Technique Center of Excellence. But this is my own work that I'm going to be presenting for today. And while it is very technical, I'm going to try to do an introduction at the beginning that's not so technical and then kind of speed along to the end. So there's a bunch of math hidden in these slides, but we'll try to keep it to a minimum here. Here we go. All right, so my applied motivation. So this is a research project, but first and foremost, it's an applied research project. So I want to keep to why I'm actually doing a whole bunch of math here in the middle. So aircraft have turnbuckles on them. So we're going to be doing something kind of involved in safety and reliability. So turnbuckles hold things in place for an airplane. And when the turnbuckles fail, it can cause death or injury to personnel below. So you can picture, something up above, two pieces of metal in the middle, and then another large, perhaps an engine, perhaps cargo, something attached to an aircraft. And if you've got these two little metal pieces and one of them breaks, the other one is going to hold on for as long as it can, but eventually it too will break. And if this happens while the airplane is in the sky, this can cause massive damage, whether it be to things on the ground or people on the ground. And we don't know exactly, because the turnbuckles are next to each other, how they're going to fail or what's going to happen. So we want to be able to prevent this as much as possible. So assumptions, again, research, I have to make some assumptions up front, and we've got quite a few because otherwise I couldn't do the math in the middle. So first of all, talking to SMEs, right, about my particular aircraft, we decided that these were going to be Weibull distributed things. So I don't know anybody background in reliability, but Weibull distribution is a very common thing for reliability. You can also change it to be the exponential distribution by messing with a couple parameters. But we're going to assume, for the sake of argument, that everything is Weibull distributed for my components. Then two, my components, these turnbuckles, have a stochastic dependence between them. So that means when one fails, the other one is going to fail faster. Not surprising. And in the case when I only have the two turnbuckles, all the pressure and weight is going to be on that one. So we expect that it's going to have an increased hazard rate or failure function associated with it. And we have to figure out what that looks like. And then finally, I made another assumption here at the bottom. And again, this is to make the math work. And the SMEs agreed with me that we're going to have the same shape parameter for the Weibull distribution. So while the hazard function and the rate at which something is failing is going to change over time, we're not changing anything else about the distribution of the components. So the purpose of my research, I want to create that maintenance plan, right? I want to be able to tell folks that are working with this system when they need to change out the turnbuckle. So if one's failed and they notice it, that's great. They might not necessarily know exactly its time of failure, but it's not like, oh, this one's failed, we need to immediately replace this component. Because if it fails and it's in the air, they need to know if they need to bring it down right away or if it can keep on flying for a little while with just the one turnbuckle up there. So I want to create a survival function so that I can actually map out a maintenance plan for them, and they can decide how many time units and what the risk is that they're willing to accept. Then I want to be able to work more in here. So the exact scenario that I'm going to be working towards for my particular program only has the two turnbuckles. But then we kind of got a little further and they're like, well, what if we had three? What if we had more? So the purpose could be to extend them. And I'm not going to cover this in depth. I covered it in my dissertation, but we don't need to go into that much depth here. And then finally, I want to do prediction of survival rates, right? Because we're all about, in the applied world, the prediction of things. So why is this important? Well, there's a lot of research out there that's been done, but it's all been done knowing the correlation structure between things. Obviously, probably not on aircraft in particular, but for reliability structures, you can see that the dependence is there. And we don't necessarily know, because we don't have the data to back it up, what the correlation is between those two things. And we can't usually measure it because, as I said, turnbuckles breaking in the air, they have no idea what is going on up there. They just know that now the piece of cargo is hanging somewhat half off the plane. So I don't want to assume any correlation structure in the background. I just want to be able to figure out what the time is that you need to fix one once I see that one has failed. So a little bit of background about reliability, for those of you that might not be familiar. We're working with components in parallel. So what that means is that you've got kind of a redundancy going. So up here, I've got a 3 component system, and the 3 components are all in parallel. If one of them fails, the other 2 will kind of hold on there and make sure that the system is still running. If 2 of them fail, still good. If all 3 of them fail, your entire system's going to go down, right? And this is this is the opposite of what happens when things are in series, where you have to have all of them up at the same time in order for the system to function. So a little bit of math. I warned you. Going to be a lot of formulas up here. These are the simple formulas. This is talking about how you actually measure the reliability for systems in parallel. So if you're going to figure out system reliability, which is that R sys up there, it's 1 minus the chance that you're going to fail, right? So we have failures, and we have whether it's not survival, and they're inverses of each other. So one minus the other, right? We can go back and forth. And if you've got a whole bunch of components operating in parallel, all I need to do is figure out what their individual failure rates are and multiply things together. It gets a little more complicated if you go to k out of n for the system to work. So this means that I need to have so many components operating, maybe more than one, right? But I have a whole bunch streamed up. So you can also do the math on this. For those that actually recognize the distributions, this looks like binomial, right? You've got that little binomial thing in the front. And I end up using a bit of this math in the dissertation. Okay, so a little bit about the Weibull distribution. So you can see the crazy spaghetti plots that I made up there. The fancy blue one on the side there, light blue, looks like the exponential distribution. And I kind of mentioned this. So a lot of times in reliability, you end up measuring things as an exponential distribution, usually for ease. But the problem with that is that it is making an assumption that you have a constant hazard rate, right? A constant rate of failure, no matter what happens. And it has this independence built into the background. And as we discussed, that doesn't really work for this scenario because there's dependence between my 2 turnbuckles. So instead, the Weibull allows me to kind of make a lot of different shapes, if you will, with all of the different spaghetti curves. And over here, I'm plotting out the PDFs, but I've got a whole bunch of different functions over there on the side. So the top one is known as the cumulative distribution function, or the CDF. The second one is the PDF, so the plots. The third one is the reliability function, or survival function. That's telling us how long it's going to last. And the last one is the hazard function. So you can see that these all have a whole bunch of parameters in it. For those a little more in the know with the distribution, I'm using the 2-parameter Weibull. No reason to use the 3. We don't care about the mean or where it's located. That's going to work itself out on its own. Okay, so the meat of it. Setup. I've got my 2 turnbuckles independently tested, and they're Weibull distributed. So when I start out, they're both up there, but I get to assume a little bit of independence, which is handy because it's going to make the math a whole lot easier. So then I'm going to say that I know that one of them is going to fail first. They're not going to fail at the same time. That would be too handy, although maybe not a good thing because then you're going to just have cargo falling out of the sky. But the math says that one of them is going to fail first. So instead, I am going to try to figure out what this looks like. And I can set it up using my CDFs of my Weibull distribution. Again, lots of math. So if one fails first, what I can do is decide that, okay, the one that fails first is going to be the minimum, right? So we know that minimums are order statistics. And it's the first order statistics for that set. So if we use a little bit of intuition and everything, I can get it down to say that the minimum, conveniently with my derivation here, is also going to be distributed Weibull. So I can use that 2, right? That 2 is coming from the fact that there are 2 components when I start. And now I have a little bit more insight into when the first one is going to fail, because it is that minimum. But I don't actually care about the first one. I care about the one that's left over. And unfortunately, the math for that is a lot more complicated. So why is it more complicated? Because I've increased my hazard rate. So here I've got a theta and a lambda, and I know that the hazard rate of my second component is going to be greater than the hazard rate of my first component. You guys can just trust me on that, or you can take that and work through the little algebra that you'd have to do on the side. But we know that the second component, I'm going to call it L. So the first one that failed is going to be M, our minimum, and the second one is going to be L, our leftover, last, whatever term you want to use for that. And it's going to have a constant rate because it has a constant pressure being put on it. But from the exact time that that first one breaks, it has that increased rate. And I need to figure out what that rate is. And if all I know is that it's going to be bigger than the first rate because the pressure is greater, then that's what I'm going to work from. And you can see kind of the, again, spaghetti plot on different possible hazard functions. So hazard functions are just the rate at which it's failing. So I'm going to use conditional and joint distributions, lots of probability theory lurking in the background and lots of scary math. And this is just, again, working from all of the information that I already know. The really messy part of this research was the bottom part. So the identity functions tells you the dependence between things. And math is really easy when things are independent, but here they're not independent. And so I end up with a dependent structure between my L and my M, which you can see kind of on the side in the identity function. And the L is dependent on when M failed, right? And it is done so by the hazard rates. So one component had a certain hazard rate going forward. They shared the same hazard rate. And then once one broke, I replaced it. And I need to know what that timing is without knowing the exact time that something failed. So instead, I do all this fancy math. And I figure out that it has a shifted failure rate. So I'm going to shift it over, right? Shift the starting time of my original component over some amount, and then it's going to start its new lifetime. This will make a little bit more sense when I pull up a picture later with a bunch of like lines and things. It's more than 2 components, but I think it kind of helps explain. So it is not actually, strangely, the failure time for the second component. It's not going to give me that. It's going to give me that lifetime that it had after the first one failed, which could be handy. But again, we would need to know the exact moment of failure of the first one, which we don't. So I'm going to have to do even more math on the backside after I figure out how to get the L. And that is to be this T. I want to know when the whole system's going down, right? Maybe I don't care about the individual failure times, but I want to know for sure when I'm going to have to replace that thing. And so this is going to let me measure that. Okay, so that means that I have to calculate a joint distribution. Again, a lot of math hiding in the background here. And I'm going to redefine a relationship beta to be the 2 hazard rates over top of each other, just kind of for ease of looking at this. And unfortunately, I've looked at this long and hard, and I really, really wanted it to be Weibull distributed, and dang it, it's not. So instead, I'm going to have to make a whole bunch of new assumptions and push forward with all my calculations to try to do integrals on this thing. So here's the integral, and I can get a closed form solution for it only in that special case of gamma equals 1. What's gamma equals 1? Exponential, which is done a lot out there. So if you, again, know anything about reliability, you can do this pretty easily if you've got the exponential distribution. But I said we didn't really want the exponential distribution because that assumes that the hazard rates are the same. And on this particular thing with the aircraft, my hazard rates are not the same. I have a greater pressure exerted on the other one. So that's not going to work. And I don't have any closed form solutions when this is not an approximation. Normally you'd take and run Monte Carlo simulations on this, and we can do that, except that's not going to give me a nice survival function for the program office to look at. So I have to figure out something else that's going to give me kind of a quantitative response more than just Monte Carlo. So instead, I end up doing a crazy amount of Taylor series expansions. So I have this, again, lots of crazy math up here, but it works. It cannot be further collapsed down to anything nice, unfortunately, because of all the crazy binomial coefficients. If you do all the math out and write everything in terms of factorials and everything, it gets super messy. And you also have to do an assumption that 0 to the 0 power is 1. Don't shoot me. It works, I swear. But there's the math on this. But this is actually going to let me calculate that survival function that the program office wants to see. And then if I so desire, I'm not going to go into all the depth of details on this, but I could look at system failure times for the whole system for more than 2 components, right? So I kind of alluded to this. So if I have k out of n components, you can extend this out. The math is not that bad. It's dealing with multiple shifts, right? So every component, you have a whole bunch of minimums in a row. Each one is going to fail in that pattern. And then you're going to shift it over by the failure rate that changes, because the failure rate is going to go up every time I lose a component. Now, I have gotten the question, what happens if you lose one in the middle? Isn't it going to put more strain on the sides? We did not get into that. So you assume that it puts the strain evenly across. Think of like backpack straps where it's just going to pull the whole thing down more. So this is the visualization I was talking about, and it might help a little bit more than just me waving my hands up here. So picture this one is a 4-component system instead of a 2, because the 2 was kind of boring. The total lifetime of the system, T, is made up of the lifetime of each of the minimums, except I already said that they're going to fail at some point, and it's going to have that additional strain put on it. And I can't just add them all up together. I have to handle the fact that M1 was operating with M2 in parallel for a while, and M3 and L, right? So we had all 4 of them at the beginning. So I have to actually subtract off that extra part. And I don't know where all those black dots are along the side. Now, technically, they all started back at the beginning and they were all operating, but they weren't all operating at an increased rate. And so each of these betas take into the fact that I have an increased rate pulling on all of my things in parallel. So I want to figure out when that overall time is, and the approximation lets me do so. And in case anybody is really interested, this is what it looks like if you do it all out for the K thing. So you get a whole bunch of integrals. It gets crazy off the page, but you can still do the math, and this one is all Monte Carlo all the way, no approximations. All right, so I said we wanted to have the application, and I'm going to go back to my aircraft and the cargo. So the maintenance plan requires that I have a CDF, cumulative distribution function, and then I also have a survival function for my 2-component system. So math's messy, but it's up there. I can only do this with the approximation equations, and so that's what I'm using. All the 2's that you see are a product of the fact that I have those 2 components. So don't just go replacing them with 3's and think it's going to work the same, because the approximation doesn't. But for our 2 case, it is really nice, because then I can create these curves for the program and they can decide their risk. So here is my maintenance plan. I have picked some notional numbers up there. So recall that I have to have a lambda greater than my theta. Sorry, got to get my numbers right here, because I have an increased hazard. And then I can pick anything I want to be my gamma function. So I've got my 3 values up there, and you can see with time what the probability of system failure is, right? So for example, at time 1, no probability of failure. Everything is great. You don't really need to worry about your system. However, if you're up there and you're at time 4, your system has probably failed and your cargo is laying on the ground somewhere, because both of your components have probably failed. Now, I fail to say what time is, right? Because this could be different for any number of systems. Could be hours, could be days, could be years. I have no idea. Again, all notional. But it lets them determine how often they want to do this fix and maintenance on their aircraft. So for example, if you only want to have a 20% chance of system failure, DoD wide, right? So 20% is pretty good. Then for the given parameters, I would say that you should replace your system and do maintenance at 2.43 time units, whatever that is to you. So program really likes this, right? Because it lets them categorize their risk associated with the pylon failure, or turnbuckle failure, rather. So empirical system failure times, I can also map out when I think it's going to fail. So in addition to the beautiful CDF curve, I can plan this out for empirical data and say, okay, your system failure times are actually going to look like this. Does this look like a distribution? Yeah, I could probably put a distribution on it and actually fit that in there. And I put a smooth curve on to show that. But it's not a natural distribution. It doesn't follow a Weibull exactly. It doesn't follow a normal exactly. Not a log normal, nothing that I can work with. But I can at least map it out and overlay it with the PDF for them to play with. And then in case we wanted to see something else with some different values, I've plotted another one. This one's a survival curve. As I said at the beginning, survival is just the inverse of the CDF. So instead of looking and seeing when it's going to fail and having that increase over time, I have it decrease over time, right? So probability of survival starts at 1, and then this is a much more extreme case. And by 3 time units, the system has definitely failed, right? So again, either one of these can help them determine their maintenance schedule. And if in this case they maybe didn't care as much and they're like, okay, 50% chance of survival is fine, then you should take your maintenance action at 1.17 time units, right? So they can just work on this graph and use it to trace back exactly what they want to do. So conclusions. I don't have to have a correlation structure. So when I started this, it was a big deal for me finding papers in that a lot had been done out there with knowing what it's going to do when I break one, this one is going to react thusly. It's like, well, that's great, but that doesn't really work for our aircraft because we can't measure that. So this actually lets us figure that out for the 2-component system. And in most of the aircraft cases, we do only have the 2 pylons attached. So program is like, that's great. I can make my maintenance plan now. And then conveniently for me, you can't extend this. So as I had said and put the crazy formula up there, if I want to do K out of N failures, you can calculate that as long as you're assuming that they're all going to have the same rates across. And then if the Taylor series holds, then you can use those survival curves and just construct your maintenance schedules. You don't actually have to do any of the crazy math. You can just plug it into, it's one simple equation that I've narrowed it down to, and you can simply plot that and pull it up. And that's the end because I flew through the math. So,
thank you. This is really nice. Thank you for doing all the math for me. I have one question. And you may have said this, and I'm sorry if I missed it. When you were doing the original calculations of the reliability of the straps, the individual straps, right? I assume you're doing some sort of testing to failure to parameterize the Weibull. Were you doing those on single straps, like when they fail when they're by themselves, or were you doing it when they fail when they're working in pairs?
Good question. I don't think I answered that, and it's in pairs.
Oh, good. Okay.
Yeah.
All right. Thank you.
Yeah. So anytime they have the individual, and I'll go back to my picture. Anytime they have that, I have to do everything with the M1. And so however many we've got, I've got to have that many up there. And then you see when they fail, because that's the only time that they're actually independent. Now that I've lost the whole room. Yay.
Okay, so when choosing, I guess, your distribution, I like to think of, if I'm going to try and maybe model a process, thinking about certain maybe constraints where, okay, I'm going to assume that nothing's going to fail at time 0 and so therefore any distribution I pick should at least be 0 at time 0. Did you do any of that?
Yeah, so the Weibull itself, and along with the exponential, gamma, beta, you can set your time points for those. and Weibull exponential start at 0 automatically. So you can never have anything negative. It's why we don't use the normal typically for reliability calculations. But the easiest way to do this is if you're trying to fit a distribution at the beginning, if they'll give you data and you can actually calculate the time curves, you can plot it out and jump handily enough. I know Tom Donnelly was in the audience. You can have it fit the distribution, and that's where you'll get those parameters too. So the Weibull is one of the most common for reliability, but you can fit anything and have it start just at 0.